Number system conversions. So here I am considering decimal, binary, octal, hexadecimal. Okay, I will convert a number from one number system to other. So how many conversions you will get? Any other? 12. Yeah, 12 is correct. See here, first I will consider decimal number. I will convert into binary. I will convert into octal. I will convert into hexadecimal. Similarly, the reverse also. Binary to decimal, octal to decimal, hexadecimal to decimal. Total 6 conversions. And then binary to octal, octal to binary. Then binary to hexadecimal, hexadecimal to binary. And then octal to hexadecimal and hexadecimal to octal. Total 12 conversions. Here decimal to decimal, binary to binary, octal to octal, hexadecimal to hexadecimal, we won't do that conversion because we will get the same number, right? So here repetition is not allowed. That means total 12 conversions we will get. First one is decimal to binary conversion. See here in the decimal we can represent 0 to 9 for a single digit, right? In the base 2 binary number system we can represent either values 0 or 1, right? So here we can represent only two values 0 and 1, but here we are having 0 to 9. Here base is 2, binary base is 2. Okay, whenever you are dividing any number with 2, what are the possible remainders? Yeah, 0 and 1. That means what? We are getting binary numbers, right? So here we'll do the repetitive division with this particular base, right? So here I am considering 40 is the decimal number. I want to convert into binary. 40 is the decimal number. I want to convert into binary. Here I will do the repetitive division. 2 20s are 40, remainder is 0. 2 10s are 20, remainder is 0. 2 5s are 10, remainder is 0. 2 2s are 4, remainder is 1. 2 1s are 2, remainder is 0. 2 zeros are 0, remainder is 1. Till I get here 0, I will take all the remainders. Okay, and all these remainders I will take in the reverse order. That means whatever the remainder I got first, that will be the last. Okay, whatever the remainder I got last, that will be the starting, like that. So here I will write 1 0 1 0 0 base. This is nothing but 40 base. Whenever we are dividing a number with 2, then we are getting the remainders as either 0 or 1, right? So here in order to get the binary number, here I am doing repetitive division with 2. And whatever the remainders I got, those remainders I will take in the reverse order. That means whatever the last remainder I got, that will be my first bit. Like that, 1 0 1 0 0. So I will continue this repetitive division process till I will get here 0, like that. Okay, next, decimal to octal. Here in octal base is 8. So here we will do the repetitive division with 8. Here we are converting decimal number into binary. Here base is 2. That's why I have done repetitive division with 2. So that I got the remainders as 0 or 1, right? Here I want to convert decimal number into octal. Here base is 8. Do repetitive division with 8. 8 5s are 40, remainder is 0. 8 zeros are 0, remainder is 5. So take the remainders in the reverse order. That means this will be the starting 5, this will be the last. 5 0 base 8. This is nothing but decimal number 40. Here we are getting the octal digits 5 and 0. Okay, regarding that real number we'll discuss little later. First I am considering for integer part and then fractional part, and then I will come to the real number. Next one is decimal to hexadecimal. In hexadecimal base is 16. So here we have to do repetitive division with 16. Okay, convert this decimal number into hexadecimal. What will be the answer? So here we have to do repetitive division with 16. 16 2s are 32, remainder is 8. 16 zeros are 0, remainder is 2. 2 8 base 16. Okay, so here first we have converted for integer part. I have taken one decimal number 40. I have converted into binary. I got like this. I have converted into octal. I got like this. Similarly, I have converted into hexadecimal. Here we have done for integer part. For integer part, we have done repetitive division. Repetitive division. Now we will consider the fractional part. For fractional part, we have to do repetitive multiplication. Here I am considering the remainders. There I will consider whatever the integer value I am getting to the left of the radix point, I will consider that one. Here I am considering in the reverse order, there I will consider the normal order. Suppose I am considering 0.25 base 10. Here I am having fractional number 0.25 base 10. I want to convert into binary. Previously I have done for integer part repetitive division. Now we are having the fractional part. Now we'll do repetitive multiplication with 2. 0.25 into 2, that is 0.50. After doing multiplication, whatever the value here I am getting, that value I will consider. Matlab I will take that one. So here I will take 0. After taking 0, the equivalent value doesn't change. So I will be having the same 0.50. Multiply with 2. Here I will get 1.00. In this case, I got 1. That 1 I will take. After taking 1, here it will be 0. 0.00. When you are getting here 0, you can stop the process, or based on the given choices, whether after point, whether you want 3 digits or 4 digits, so accordingly you will perform the repetitive multiplication like this. So here whatever the integers I am getting, I will consider the normal order. That means here 0 point, whatever the integers I am getting here, I will place after the radix point. So that means 0.01 base 2. This is nothing but 0.25 base 10. 0.25 base 10 is nothing but 0.01 base 2. See here I have considered the fractional part, that is 0.25. Here we have to do repetitive multiplication with the base, whichever you wanted to convert into, right? So 0.25 into 2 is 0.5, right? So after doing multiplication, whatever the integer value I am getting to the left of the radix point, I will take that one. Here I am taking that 0. After taking 0, the equivalent value doesn't change, right? So you will be having same 0.50 only. Into 2, that is nothing but 0.5 into 2 is 1, right? So 1.00. In this case, I got 1 to the left of this radix point. So in this case, I am taking that 1. After taking that 1, here it will be 0, right? So the moment if you are getting the entire value is 0, or based on the given choice, say after point, in the given choice, suppose if you are having 3 digits or 4 digits, so accordingly you will stop the process, right? So that means 0.25 base 10 is nothing but 0.01 base 10. See, previously we have considered the remainders whatever we got in the reverse order. That means whatever the last remainder I got, that will be the first. But here, whatever the integer I am getting here first, that I will place next to the radix point like that. And then next one like that. Convert this decimal number into octal number. Here we have to do repetitive multiplication with 8. See here, we are having fractional part, that is the decimal number. We want to convert into base 8. So here we will do repetitive multiplication with 8. 0.25 into 8. How much you are getting? 0.25 into 8. 2. 2.00 you will get. 0.25 into 8 is nothing but 2.00. So in this case, to the left of this radix point, I am having integer 2. So I will take that one. After taking 2, here it will be 0. So here I am getting 0.00. That means I am getting the answer as 0. The moment if you get 0, you can stop the process. Or based on the given choices, okay, after point, how many digits you are having, that many iterations you can do like that. So here whatever the integer I am getting, okay, that integer I will place after the fractional point. After the radix point, sir. Whatever the integer I am getting here, I will place after the radix point. That means here 0.2 base 8. Previously I got here 0, then 1. So I have placed these two after the radix point, 0.01. But here in this case I got only one integer, that one I am placing after point. So 0.25 base 10 is nothing but 0.2 base 8. Okay, next. Similarly you can do decimal to hexadecimal. Yeah, here we have to do repetitive multiplication with 16. 0.25 into 16 is 4. See, 0.25 is nothing but 1 by 4. 1 by 4 into 16 is 4. Right? So you will get 4.00. 4.00. So here I will take this 4. After taking that 4, here it will be 0.00. So I will stop the process. I will put this 4 after the radix point. 0.4 base 16. This is nothing but 0.25 base 10. See, for integer part we have done repetitive division. For fractional part we are doing repetitive multiplication. Opposite. Now combine both. That is, previously we have considered integer part and now we have considered fractional part. Combine those two. Say 40.25. 40.25 base 10 is nothing but what? 40 plus 0.25, right? So for 40, what you got earlier? Just check once. Previously we have converted the number 40, integer part. 10100, right? So 10100 is the binary number corresponding to decimal number 40. Okay, for 0.25 we got 0.01. So by adding those two, here I will get 0.01 base 2 like this. 40.25 is nothing but 40 plus 0.25. So 40 I got earlier like this, 10100. Now for 0.25 I got 0.01. So by adding those two, I will get like this. Or very simple, for integer part, whatever the binary number you got earlier, that you will place here, 10100. And similarly for fractional part, 0.25, whatever you got, you place here, like that. Okay, similarly for octal number, 40.25 base 10. For 40, earlier you got 50 in the octal, right? Here now 0.25 you got 0.2, that means 50.2. Whatever the numbers you are getting after radix point, that one you have to place here. Similarly here, 40.25 base 16, that equal to, earlier you got 28, right, for 40. So 28, here now you are getting 0.4, 28.4 base 16. Sorry, this is the decimal number. I have considered the decimal number only, right? I have converted decimal number into binary, then octal, then hexadecimal. First I have taken for integer part and then for fractional part, and then I have clubbed both. By combining both integer part and fractional part, I am getting the real number. The decimal number only I have converted into other number systems. Next one is binary to decimal. Binary to decimal conversion. See here, suppose you are having the decimal number, say 195. This is a decimal number, right? We are calling this particular number, right, 195 or 195, right? So what is the physical significance behind this one? See, you are having 3 digits, 195. Those 3 digits combined together, we are calling it as 195 or 195, right? What is the physical significance? Yes, 100 plus 90 plus 5, right? Very nice. See here, we are having the decimal number, right? So its position weights are 10 power 0, 10 power 1, 10 square, right? So here, each digit we have to multiply with the respective position weight and then we have to add. So here what we are getting, 10 square is nothing but 100 into 1 plus 10 power 1 is nothing but 10 into 9 plus 10 power 0 is 1 into 5. Okay, so here you will get 100 plus 90 plus 5. So after simplification you will get 195. So that means here you are having the digits 195 of decimal. Okay, after doing this simplification you are getting the same result. Because here base is 10, that's why we are getting like this. That's why whenever you are having in the decimal number systems, what are the digits we are having? The equivalent value we can say. Suppose here 195 is there, 195. That one we are calling it as 195 or 195, right? But the same thing, matlab, just by looking at the numbers, suppose if you are having 2, 3 of base 8, we cannot call that number directly 23 because the equivalent value will change. Here we are having the decimal number, that's why base is 10 here. So after multiplying with the respective position weights, and we are getting the same resultant number. Okay, here by looking at the 3 digits 195 of decimal number, we can call it as 195 or 195 like that. But if this number is belong to suppose octal, there you cannot say 195. You have to call digit by digit, like 195. Of course 9 won't come in octal, but suppose some other number is there, say 175. Okay, so if it is belong to say octal number, there you should not say 175 or 175 because equivalent value will change. We'll see how it is little later. Okay, so here I am considering binary number. Binary number, say 10100. I want to convert this one into decimal. I want to convert this binary number into decimal. See, earlier you are having 3 digits of decimal number. Here I put the positional weights in powers of 10 because here base is 10, right? And then I have multiplied each digit with respect to positional weight and then I have added. Similarly here, in order to get the equivalent value, here base is 2. So I will put the positional weights in powers of 2, right? So here it will be 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4 and then 2 power 5. So here we have to multiply each digit with respect to positional weight and then we have to add. But since we are having binary, either zeros or ones possible, right? So whenever you are multiplying any positional weight with 0, the resultant value is 0. After adding 0 to the resultant sum, equivalent value doesn't change, right? So here whenever you wanted to find out the equivalent value, right, of the binary number, just find out the positional weights corresponding to wherever the bit value is 1. Wherever the bit value is 1. Just consider those positional weights and add. Right? So here 1 is present in 2 positional weights, that is 2 power 5, another one is 2 cube. Add these two, you will get the resultant number in decimal. 2 power 5 is 32, 2 cube is nothing but 8. So 32 plus 8 is 40. So this is the decimal number. 40 base 10. In the decimal number, we are having positional weights 10 power 0, 10 power 1, 10 power 2. In order to get the equivalent value, we have multiplied each digit with respect to positional weight. And then we have added. Right? Similarly, I am having binary number. In order to get the equivalent value, I have placed the positional weights in powers of base 2. Okay, after that, I have identified wherever ones are there. Those positional weights I am adding. So that I will get the equivalent decimal number. Similarly, next one is octal to decimal. Here I am considering 50 base 8. I want to convert into decimal. Here positional weights are 8 power 0, 8 power 1. Multiply each digit with the respect to positional weight. So here I will get 8 into 5 plus 0. Right? 8 into 5 is nothing but 40. So that is the decimal number. 40 base 10. Similarly, you can do hexadecimal to decimal. Next one is hexadecimal to decimal. Convert 28 base 16 into decimal. What is the number you are getting? 28 base 16 convert into decimal. See here position weights are 16 power 0, 16 power 1. Right? Multiply each digit with the respect to position weight and then add. 16 power 1 is nothing but 16 into 2 plus 16 power 0 is 1, 1 into 8. So 32 plus 8, that is nothing but 40. So this is the decimal number, 40 base 10. Yeah, for integer part, we will start the positional weights starting from powers of 0. Base power 0, base power 1, like that, for integer part. See, very simple. See, in the binary, base is 2. Base is 2. For a single digit, you can represent 0 or 1. Right? So, when you are adding, suppose, 2 numbers in binary, then what will happen? If the resultant sum, if you are able to represent with the single bit, that means if the sum is less than 2. See, if you are having the single digit in binary, okay, you can represent either 0 or 1. Okay, I am adding 2 single bits, then what will happen? If the resultant sum is less than or equal to less than 2, if the resultant sum is less than 2, that means either 0 or 1, then I can represent with a single digit. But if the sum exceeds 1, then I require one more digit, right? See, suppose you are adding, first I am considering decimal numbers. Say 9, 5, I am adding decimal numbers, okay? After adding 9 plus 5, 14 you are getting, right? That 14 you cannot represent with a single digit because that exceeds 9, right? So here we are writing like this, 14. This 14 actual meaning is 10 plus 4. Here 10 is the decimal number base. Decimal number system having the base value 10. 10 plus 4, right? So that means here what you can say, 1, 4 base 10. Here position weight is 10 power 0. Here position weight is 10 power 1. So I am adding 2 decimal digits. Okay, if the resultant sum is less than or equal to 9, I can represent with a single digit. If sum exceeds 9, I require one more digit. That is nothing but carry. So equivalent value of that particular carry is nothing but the base of the corresponding number system. Here base 10, right? So 1 for base 10. So here base is, here this particular digit having position weight, say 10 power 0, then 10 power 1, like that it will go. Similarly here, I am adding two single bits, 1 and 1. Okay, 1 plus 1 is 2. 2 is the decimal number. But in binary, how will represent? 1 0. Okay, here this 1 0, you can write it as 2 plus 0, because this 2 is base of binary number system. 2 plus 0. So here I am placing 1 0. Here base is 2, 2 power 0, 2 power 1. 2 power 1 into 1 is 2. Equivalent value is 2. And then 0. So here sum is 0, carry is 1. Like that. So that's why, see, whenever you are having the single digit, obviously you will be having the position weight is in terms of power 0. Like suppose if base is 2, 2 power 0. Similarly, if octal number, 8 power 0, like that. Because if you are having the single digit, the equivalent value should not change. Right? So when you are having a single digit, the equivalent value will be the same. Suppose in the binary, the bits 1 and 0 are valid. Right? The same 1 and 0 are valid in all the higher number systems. Like base 3, it is valid, base 4, it is valid, base 5, like that. But the equivalent value is same when you are considering that particular digit in the least significant. Suppose I am considering 1. Okay. So here, if you consider this is base 2 or base 3 or base 8 or base 10, all those equivalent value will give 1 only. Because here I am considering 2, say 2 power 0, here 3 power 0, 4 power 0, like that. But the moment if this particular bit is in different position, then based on the position weight, the equivalent value will change. Okay, right. So that means suppose 7 is there, single digit, that 7 is valid in octal number system, the same 7 is valid in base 9, base 10, like that. So this is for integer case. We have converted binary to decimal, octal to decimal, hexadecimal to decimal. Right? Suppose fractional part is there. Suppose I am considering first decimal only. Say 0.23 you are having. This is the decimal number. Right? So here position weights will be negatively increasing powers of 10. Because here base is 10. So here 10 power minus 1, here 10 power minus 2. When you are having positive, when you are having only integer part, then the position weights will be powers of base 10, right? But when you are having fractional part, for that you will be having negatively increasing powers of base 10, like that. So here what will happen? Multiply each digit with the respective position weight. 2 into 10 power minus 1, that is 1 by 10, plus 3 into 1 by 100. So LCM will be 100. Okay, 10 into 2 is 20 plus 3. So 23 by 100. So after doing simplification also you are getting the same thing, 0.23 base 10. This is for decimal number. Decimal number I have considered. After doing, in order to get the equivalent value, the same thing I am getting. Because here base is 10. Similarly, in the binary, if you are having fractional part, there I will consider negatively increasing powers of 2. Similarly for octal number, negatively increasing powers of 8. Similarly for hexadecimal, negatively increasing powers of 16, like that, for fractional part. Okay, so with this understanding, let us directly do the, okay, first let us see for the fractional part for one case. Say 0.01 base 2. I am considering fractional part, 0.01 base 2. So here position weights will be 2 power minus 1, 2 power minus 2. Here I am having only single one under the position weight 2 power minus 2. So multiply, you consider only that particular position weight because you are having only one position weight. Okay, where the corresponding bit is 1. Right? So 2 power minus 2 is nothing but 1 by 2 square, that is nothing but 1 by 4, which is nothing but 0.25. For integer part, from right hand side to left hand side will start the positional weights in the increasing powers of the corresponding base. Like if it is a base 2, 2 power 0, 2 power 1, 2 square, like that. Right? For fractional part, just after the radix point, okay, the positional weights will be negatively increasing powers of base. Here base is 2, so 2 power minus 1, 2 power minus 2, like that. Yes, see, if you put here position weight, it will be 2 power 0. So 2 power 0 into 0 is 0 only. So you will get 0 only here. Here 0 you are getting. 0 into 2 power minus 1 is nothing but 0. Then 1 into 2 power minus 2 is 2 power minus 2. After simplifying, you will get 0.25 base 10. Okay, so here first we have considered for integer part, then for fractional part individually. Even if you are having direct number, suppose I am considering the real number. That means previously I have considered 10, 100, and then here I am getting 0.01. Okay, so I am directly considering the real number, right? So now if you are having direct real number, what you can do, first you observe the radix point or base point. To the left of that one, you put position weights in the increasing powers of the corresponding base. Here base is 2, 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5. For fractional part, you put negatively increasing powers of 2. Like 2 power minus 1, 2 power minus 2, like that. So here we already found out, here for integer part we got 40, for fractional part we got 0.25. So directly you will get. So if you are directly having the real number, directly you can put the position weights like this. Okay, start from the radix point to the left, increasing powers of the corresponding base. Okay, for the right hand side, negatively increasing powers of the base, like that. Okay, so with this understanding, let us directly do for the real number, for octal to decimal. Say 50.2 base 8. 50.2 base 8. See here position weights are 8 power 0, 8 power 1. Here position weight will be 8 power minus 1. Okay, so 8 into 5 is plus 2 into, or you can write 8 power minus 1 into 2. Okay, so 8 5s are 40 plus 2 by 8 is nothing but 1 by 4. That is nothing but 0.25. So 40 plus 2.25, that is 40.25 base 10. Okay, so whenever you are getting direct real number, directly you can do the simplification. Just put the position weights and then multiply each digit with the respective position weight and then add. Yeah, 40.25 is the correct answer. Next, similarly do for hexadecimal to decimal. 28.4 base 16. Convert this one into decimal. Convert this hexadecimal number into decimal. 28.4 base 16. Here you have to put the position weights in powers of 16. Yeah, 40.25, right. 16 power 0, 16 power 1, here 16 power minus 1. 16 2s are 32, plus here 1 into 8, plus 16 power minus 1 into 4. 16 2s are 32, plus 8, plus this one you can write it as 1 by 16 into 4. 4 4s are 16. So 32 plus 8 is 40, plus 1 by 4 is nothing but 0.25. So you can write 40.25 base 10. 28.8, that is the hexadecimal number. We have to convert into decimal. Okay, so put the position weights. Here 16 power 0, 16 power 1, here 16 power minus 1. So here you will get 40, 16 2s are 32 plus 8 is 40, plus here A is 10, 10 by 16. Do the simplification and then you will get the equivalent value. This is hexadecimal to decimal. Because we cannot represent 10 with the single digit, that's why I have considered alphabets A to F. So up to now we have done 6 conversions. That is decimal to binary, octal, hexadecimal, and then the reverse conversion. Right? Now let us do the other 6 conversions. Binary to octal. Now let us do the binary to octal conversion. Here in the binary base is 2, in the octal base is 8. How we can write 8 in terms of 2? 2 power 3, right? 8 we can write it as 2 cube. 8 we can write it as 2 cube. That means if I consider 3 bits of the binary number, 3 bits of the binary number, then I will get the corresponding octal digits like that. So here I am considering binary 3 bits. Okay. So when you are having, see, when you are having a single bit, you can represent with either 0 or 1. Like that, here we are having 3 bits. So all those 3 bits you can represent in terms of zeros and ones. Like that, 8 combinations you will get. So write down all those 8 combinations of zeros and ones. These are the 8 combinations of zeros and ones. Right? So now, what are the position weights? See, previously in order to get the equivalent value, what I have done, I have put the position weights. Here 2 power 0, 2 power 1, 2 square. These are the position weights. So here all the bits are zeros, the equivalent value will be 0. Next, here I am having bit value 1 under the position weight 2 power 0. 2 power 0 is nothing but 1. Right? Next, here bit value is 1 under position weight 2 power 1. 2 power 1 is nothing but 2. Next, here I am having two ones. The corresponding position weights are 2 and 1. Right? 2 plus 1 is nothing but 3. 2 plus 1 is nothing but 3. Now just observe. First four combinations, here MSB bit is 0. Right? Here I am having MSB bit is 1. Remaining bit combinations are same thing. 0, 0 to 1, 1. Right? So now bit value is 1 here. Its corresponding position weight is 2 square. That is nothing but 4. Right? So just add 4 to these four combinations. You will get the resultant value here. 4 plus 0 is 4. 4 plus 1 is 5. 4 plus 2 is 6. And then 4 plus 3 is 7. See here, I am having this particular bit value is 1. So the corresponding position weight is 2 square. It is nothing but 4. Remaining bit positions, I have found out the equivalent value earlier. I got 0 to 3. So I am adding 4 to these four combinations. So I am getting the equivalent value. Now just observe, I am considering the binary number as the input. I am getting the equivalent value like this. Okay. So for a single digit, I am getting the values 0 to 7. These are nothing but what? Octal digits. So that means whenever you want to do the conversion of a binary number into octal, okay, you require 3 bits. If you are having 3 bits, you can do the group of 3 bits. You will get the corresponding octal digit like that. Okay, first let us consider the binary number integer part. Suppose I am having 1 0 1 0 0 1 0 1 0 0. So here what we have to do? We have to do this is the binary number. We want to convert this one into octal number. Okay. So here what we got, by combining 3 bits, we will get the corresponding octal digit, right? So here I will do grouping of 3 bits. For integer part, I will start from right hand side to left hand side. Okay. So 000 is nothing but what? 0. Then 101 is nothing but 5. So 50 base 8. Okay. So for integer part, we have to do the grouping of 3 bits from right hand side to left hand side. Okay. And corresponding those 3 bits, whatever the equivalent number is there, that digit we have to place. Okay. So similarly here for fractional part, say 0.01 base 2. I want to convert into octal. Okay. Here I am having only 2 bits. Okay. What you can do? You can put rightmost side 0. If you put 0 here, the equivalent value won't change. See, just like for integer part, here in this case I got 3 bits. Okay, suppose you got say 2 bits only, but I want to do the grouping of 3 bits. So there I will put one more 0. The equivalent value doesn't change. For integer part, you can place leftmost side any number of zeros based upon your requirement. The equivalent value doesn't change. Similarly for fraction part, if you put n number of zeros to the rightmost side, okay, the equivalent value doesn't change. Right? So here you are having 0 1 0, that is nothing but 2. So this is nothing but 0.2 base 8. 0.2 base 8. So for integer part, we are starting from right hand side to left hand side, doing the grouping of 3 bits, we are getting the corresponding octal digits. Similarly, for fraction part, we'll start from the whatever the radix point is there. After that, okay, we'll start do the grouping of 3 bits like that. Okay, so now let us combine both, you will get the real number. These two numbers I am combining. Directly you can write 1 0 1 0 0 0.01 base 2. That is nothing but 50.2 base 8. We can convert the octal number into the corresponding binary number by representing each octal digit with 3 bits. Previously in the forward direction, by doing the grouping of 3 bits, we got the octal digits. Now we are doing the reverse process. That means we are having the octal digits. Now we want to represent in the binary. So here each octal digit we have to represent with the 3 bits like that. So directly consider this number 50.2 base 8. Okay, 5 is nothing but 101. Then 0 is nothing but 000. 0.2 is nothing but 010. Okay, so here for each octal digit I have represented with 3 bits. After that, suppose for integer part, if I am getting leftmost side zeros, I can remove because those zeros simply doesn't change the equivalent value, right? You can remove those zeros. Those are like insignificant. Okay. Similarly, for fractional part, if you are having rightmost side zeros, you can remove. Okay. So now next step, what I will do here for integer part, I am having leftmost side 1 only, so I will keep. But for fractional part, I am having rightmost side 0, so that 0 I can neglect. So this is nothing but 101 000 0.01 base 2. Okay, in this way we can convert octal number into binary. First we'll represent each octal digit with the 3 bits, and then for integer part, if I am having leftmost side zeros, I will remove. Okay. Similarly for fractional part, if rightmost side zeros are there, I will remove. Okay. So this is regarding binary to octal and octal to binary. Now next one is binary to hexadecimal and hexadecimal to binary. Here in hexadecimal, base is 16. Base is 16. 16 we can write it as 2 power 4. Okay, 2 power 4. So that means we require 4 bits of the binary. So here I am considering one more bit. Its position weight is 2q. So here 4 bits are there. Total 16 combinations will come. So here simply I will put 0 for 8 combinations. Okay. Next I will write 8 more combinations. Here I will put MSB bit as 1. Remaining 8 combinations of 3 bits will be the same thing. Write down all the 16 combinations of zeros and ones. Okay. Here MSB bit is 0, right? So whatever the earlier equivalent value I got, the same thing will be valued. Okay. But here if you observe, MSB bit is 1. Okay. Its position weight is 8. Okay. Remaining 3 bits, whatever the combination, here I am having the same combination. So that means here I will add 8. 2 cube is nothing but 8. So 8 I will add to this equivalent value, so that I will get the equivalent values of these 8 combinations. So 8 plus 0 is 8. 8 plus 1 is 9. 8 plus 2 is 10. Okay, so equivalent value I am getting 0 to 15. But our requirement is hexadecimal, right? So 10 to 15 I will represent with the alphabets. Okay, A, B, C, D, E, F. 10 to 15 we cannot represent with a single digit for hexadecimal, so that's why I am using the alphabets. So these are the hexadecimal digits. Okay, so that means by doing the grouping of 4 bits, we will get the corresponding hexadecimal digits. Okay, I am directly considering the real number 101,000,001 base 2. I am considering the given number 101,000,001. Right? Here I will do the grouping of 4 bits. Here I am having only 2 bits, so I will put 2 zeros. The equivalent value doesn't change. Okay. Here I will do grouping of these 4 bits, and here I want to do the grouping of 4 bits, but I am having only 2 bits, so I will place 2 zeros. The equivalent value doesn't change. Right? So 0010 is nothing but, just see here, 2. Then 1,000,000 is nothing but 8. 28.0100 is 4. 28.4 base 16. Whenever you do the grouping of 4 bits, for integer part, start from just to the left of that particular radix point, okay, to the towards left hand side. For fractional part, start from here towards right hand side, like that. Here we have to do the grouping of 4 bits because we are converting binary number into hexadecimal. See here, for representing 15 or F, I require 4 bits. See, in the hexadecimal number, maximum value we can represent for a single digit is 15. That is nothing but F. Okay, for that I require 4 bits. So that means with the help of 4 bits, I can represent all the remaining hexadecimal digits. Okay, so that's why we have to do the grouping of 4 bits. See, if you are doing grouping of 3 bits, then you will get 010 is nothing but 2. But we are doing the conversion of binary to hexa. That means you have to do the grouping of 4 bits. 28.4. Similarly, next one is hexadecimal to binary. Here we'll represent each hexadecimal digit with the 4 bits, like that. Previously we have converted octal to binary by representing each octal digit with the 3 bits. Here we'll convert each hexadecimal digit with the 4 bits. I am considering the same number, 28.4 base 16. Okay, first represent each hexadecimal digit with the 4 bits. 2 is nothing but 0010, 8 is nothing but 1000, 0.4 is nothing but 0100. After doing like this, if you are getting for integer part leftmost side zeros, similarly for fractional part rightmost side zeros, those zeros you can remove, those are insignificant. So here you will get 101000, 0.01 base 2. Okay, so in this way we can do the conversion of binary to hexadecimal and hexadecimal to binary. Two conversions are pending. What are those? Octal to hexa and hexadecimal to octal, right? See here we have to convert the octal number into hexadecimal number, right? Direct conversion is not possible. Directly we cannot do the conversion from octal to hexadecimal. What we can do, first we can convert the octal number into binary and then we'll convert the binary number into hexadecimal. Okay, write down. We can convert the octal number into the corresponding hexadecimal number by following these two steps. First step, convert the given octal number into the corresponding binary number by representing each octal digit with 3 bits. Convert the given octal number into the corresponding binary number by representing each octal digit with 3 bits. Next, second step, convert the above binary number into the corresponding hexadecimal number. Convert the above binary number into the corresponding hexadecimal number by doing the grouping of 4 bits. And representing into the corresponding hexadecimal digits. By doing the grouping of 4 bits and representing them into the corresponding hexadecimal digits. Okay, so here I am directly taking the real number 50.2 base 8. I want to convert into hexadecimal number. Here first step is, first we'll convert this given octal number into binary by representing each octal digit with the 3 bits. Okay, 5 is nothing but, so here I am writing first step 50.2 base 8, that equal to 5 is nothing but 101, 0 is nothing but 000, 0.2 is nothing but 010. First step is we have to convert the given octal number into binary by representing each octal digit with the 3 bits. Okay, next step is what? We have to convert this above binary number into the corresponding hexadecimal. So here I am writing 101, 000, 0.010 base 2. Okay, so here what we have to do? We have to convert this binary number into hexadecimal by doing the grouping of 4 bits, right? Whenever we are doing the conversion from binary to hexa, we have to do the grouping of 4 bits. So here, this is the radix point. So here I wanted to do the grouping of 4 bits, but I am having only 3 bits. So I will put one more 0 here, right? So here I will do grouping of 4 bits, but here I am having only 2 bits. So I will place 2 more zeros. Okay, 0010 is nothing but 2, 1000 is nothing but 8, 0100 is nothing but 4, 28.4 base 16. See here, for understanding purpose I am giving the 2 steps, but in the exam you can perform directly in 1 step. Like first you will convert the given octal number into the corresponding binary, that means represent each octal digit with the 3 bits, okay, and then do the grouping of 4 bits in order to get the hexadecimal number. Okay, so you will get 28.4 base 16. Okay, similarly you do the reverse conversion, that is hexadecimal to octal. Here first step is, first we'll convert the hexadecimal number to binary. First we'll convert hexadecimal number into binary, right? By representing each digit with the 4 bits. and then this binary number will convert. Okay, so here what is the answer I got? That is the hexadecimal number. So here I will consider 28.4 base 16. Okay, let us convert into octal. Whether we are getting the same number or not, let us check. Okay, so here 28.4 base 16. This is the hexadecimal number. First we have to represent each digit with the 4 bits. 2 is nothing but 0010. 8 is nothing but 1000. 4 is nothing but 0100. This is the binary number. Okay. First I have represented each digit with the 4 bits. Now, in order to get the octal number, I will consider this number. Now I will do the grouping of 3 bits in order to get the octal digits, right? So here 010 is nothing but 2. Then you are getting zeros. Okay. So I will put 2 more zeros here. I will write 0 here. Here 000 is nothing but 0. Then 101 is nothing but 5. So here I will put 1 more 0. 000 is nothing but 0. So 050.20. So this 0 is insignificant. Similarly here also insignificant. So I will write this one as 50.2 base 8. So I am getting the same answer. Okay. So up to now we have done all the conversions. We have considered what are the number I am considering from some number system. Okay. After that I have done the conversion, and whatever the conversion I got, the resultant number, the same thing I got in order to cross check whether I am getting the same answer or not. Just go through your notes. We done all the 12 conversions, right? So whether whatever we have assumed, suppose 40.25 we have considered decimal. That one we have converted into binary, octal, hexadecimal, and then reverse also we have done. And then we have done binary to octal, octal to binary, and binary to hexadecimal, hexadecimal to binary, and then octal to hexa and hexadecimal to octal. Okay, just go through your notes.